Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing one example for equilibrium with link interactions. So, let us continue that example here. So, previously we had solved this example by manually considering the cases. Okay. So, now we will be taking the help of this optimization formulation and then we will try to see whether we get the same solution or not. Now, before we can say that the solution of the optimization formulation is unique and so on. So, we had made some assumptions on the travel time functions. Okay. So, note that the first assumption that is required is that the derivative of the travel time on any link A with respect to the flow on link A should be positive. Okay. So, this anyway holds. Because if you recall, these were the travel time functions. So, T1 was equal to 2 plus 3x1 plus 2x2 here, T2 was equal to 4 plus 2x2 plus 2x1 here, and T3 was equal to 3 plus x3 here. Okay. So, if you take the travel time functions derivative with respect to flow on that link, so you will be finding that that is positive because that value will be equal to 3 in this case because of this, it will be equal to 2 in this case because of this term, and it will be equal to 1 in this case because of this x3 term here. Okay. So, that assumption holds. We also need to check if the link performance functions for these links 1 and 2, which we have assumed that they are having interactions, they are symmetric or not. Okay. So, in order to determine that, what we need to do is that we need to take the partial derivative of the travel time on the first link with respect to the flow on second link, and then we need to take the derivative of the travel time on the second link with respect to the flow on first link. Okay. So, when we do that, we will be getting 2 in both the cases here. Okay. So, this one can easily see here. Okay. So, this condition is satisfied here, that is the link performance functions are symmetric for 1 and 2. So, now let us write down the optimization formulation for this example here. So, note that if you remember, there were kind of two terms corresponding to the links in the objective function. The first term was such that we were keeping the flow on the other link which is having interaction to be constant. So, that is why we get this first term here. So, this is half times of this 2 plus 3 omega plus 2 x2. Okay. So, here we have kept x2 as it is, and since there was x1 here, so we have put it omega and omega because we are integrating with respect to x1 here, and this is the term corresponding to the other link 2 here. So, now we have kept x1 as it is, and instead of x2 we have omega here because we are integrating with respect to x2 here. And now for this first link here, there is this second term, but this is different from this first term in the sense that instead of 2x2 we have 0 here. Okay. So, that is why we get this term, and instead of the second term here we have put 0 in 2x1. Okay. So, that is why we get this term here. Okay. And then there is this last term which is corresponding to the third link here. Okay. So, there is no link interaction for the third link. So, this one is just simply coming as it is. Okay. and which subject to the constraints that the sum of the flows on both the links x1 and x2 should be equal to the total demand 5 here. Also x1 plus x2 should be equal to x3, and x1 and x2 should be greater than equal to 0. Okay. Um, we have not written x3 greater than equal to 0 because automatically if x1 and x2 are both greater than equal to 0, so then x3 will also be greater than equal to 0. Okay. So, just for the curiosity, let us check the Hessian of the objective function here. Okay. So, this is the Hessian that you will be getting here. So, again how do we get Hessian? So, we need to write down the these travel time functions here. So, 2 plus 3x1 plus 2x2, and the travel time of the second function is 4 plus 2x2 plus 2x1, and the travel time of the third link is 3 plus x3. Okay. So, here if you remember that the derivative of the travel time on any link is with respect to the flow on that link is just the travel time on that. Okay. So, this is that dz, the derivative of the objective function with respect to the flow on any link A is equal to the travel time of that link A. Okay. So, this value is then actually the second derivative of this objective function with respect to the flow on link A, but twice. Okay. So, since this is link 1, so we get this 3 value here. Okay. This value is the second derivative, but first with respect to the flow on link 1 here, and then with respect to link 2 here. Okay. So, this is then 2 here and so on. Okay. So, this is how we get this Hessian matrix here. So, this Hessian matrix is positive definite. Okay. And this you can easily check by looking at the left sub matrices here. So, you will see that the determinants of all the left sub matrices is positive. For example, the smallest left sub matrix is this 3, which is positive. Then you will have this 2 cross 2 matrix here, which is again having positive determinant. And then when you look at this larger matrix here, that is also having positive determinant. Okay. So, therefore, the solution of this program will be unique in terms of the link flows. Now, since we know that the flow on link 3 will be equal to 5, so we can actually drop the integral corresponding to x3 in the objective function. Okay, because that one is like 0 integral 0 going to x3 3 plus omega d omega. Okay, this is the last term in the objective function. So, since x3 is constant, so this will come out to be a constant. So, as you have seen many times before, if you add a constant to an objective function, the optimal solution does not change. So, we can drop this term corresponding to the third link here in the objective function. So, therefore, we get the objective function as follows. So, this we have obtained by doing the integration here. Okay. So, we had the 4 terms finally after ignoring the last term corresponding to link 3. So, when we do the corresponding integrations, this is what we will be getting here. Okay. Now, what we know is that x1 plus x2 is equal to 5. So, we can substitute x2 to be equal to 5 minus x1 here. Okay. Now, this also you can easily see that this is what we will be getting. So, one thing to notice here is that these terms are coming twice here. For example, 2x1 is 1 here and then it is also coming here. 3 by 2 x1 square is coming here and then it is coming here, 2x2 x1 is coming here and then it is coming here, 4x2 is coming here, then it is also coming here, and then x2 square is coming here and then it is coming here. Okay. So, when you will add all of these and then there is half in the outside, so you will be getting these 2x1 plus 3 by 2x1 square plus 2x2 x1 plus 4x2 plus x2 square. Okay. And then we can substitute that x2 is equal to 5 minus x1. So, this is the first term where you have x2 from the left. So, we put 5 minus x1 here. Then this is the second term where we have x2. So, we put 5 minus x1 here, and then this is that term where we put again x2 is equal to 5 minus x1 here. So, now we differentiate this objective function with respect to x1 here and then we will equate it to 0. So, this is the equation that we get when we equate it to 0. So, when you will solve this, you will get that x1 is equal to coming out to 2, and since x1 and x2 are summing to 5, so x2 will be 3. So, the optimal solution x1 star is equal to 2 and x2 star is equal to 3, and this is the same solution that we had obtained when we had solved this problem by considering different cases. Okay. Okay. So, now let us come to this case where we have the generalization to multi-link interaction. So, until now we were only considering the case when there are interactions between two links here. So, now let us generalize this. So, now the travel time on a particular link may be a function of the flow on several links, not just the flow on the opposite direction link. Okay. So, this can be mathematically represented that TA is not just only the function of xa, that is flow on that link, but it can be function of the flow on several other links as well, and that vector here is represented by this x here. So, we will be considering the case where the link interactions are symmetric. Mathematically, that means that the partial derivative of the travel time on link A with respect to the flow on link B will be equal to the partial derivative of the travel time on link B with respect to the flow on link A. Okay. And this holds for every pair of links A and B which are not same. Okay. So, for example, if there are 3 links 1, 2 and 3 here. So, what it means is that the travel time derivative on the first link with respect to the flow on suppose the second link is equal to the derivative of the travel time on second link with respect to the flow on first link. Okay. And the derivative of the travel time on the first link with respect to the flow on third link is equal to the derivative of the travel time on third link with respect to the flow on first link. Okay. So, we can keep writing down these equations. Okay. So, these ensure that the link interactions are symmetric. So, note that when there is no interaction, that is the case that we had considered first in the equilibrium, that there are no interactions between various links. So, then also this case holds, as then the derivatives will be equal to 0. Okay. So, again this generalization is an extension of the first equilibrium case that we had considered, user equilibrium, where there are no link interactions. Okay. So, there all of these terms were actually equal to 0. So, this equation even holds there. Only when these terms are non-zero, then actually we are meaningfully considering these multi-link interactions. Now, note that this condition here is a requirement that the Jacobian metrics of the link performance functions are symmetric. Okay. So, if you remember what is Jacobian metric, so if you have a function given and when you put together all the partial derivatives of that function, then that is a Jacobian matrix. Okay. So, this condition actually implies that this Jacobian matrix of the link performance functions will be symmetric. This Jacobian matrix is denoted by uh, this matrix here, and it includes the partial derivatives of all the link travel times with respect to all the link flows. Okay. Suppose there are A links in the network. Okay. So then this is how the Jacobian matrix will look like. Okay. So we have the partial derivative of the travel time on first link with respect to the flow on link 1, then we have the partial derivative of the travel time on link 2 with respect to the flow on link 1, and so on. Okay. So this is how it will look like. So for the cases where the above symmetry condition holds, the one which we just saw, that is this condition, so an equivalent optimization program can be formulated to find the equilibrium flows. Okay. So this condition is equivalent to saying that this matrix is symmetric. Okay. So under this case, we can formulate this multi-link interactions as an equivalent optimization formulation. We are not discussing that optimization formulation here because that is slightly involved, but one important aspect that we discuss here is that the Hessian of the objective function in that optimization problem is actually the above Jacobian matrix. Okay, so I mean we are not telling that why that came suddenly, but let us assume that the Hessian matrix of this optimization problem that exists for this multi-link interaction case is actually the Jacobian matrix which is shown here for the travel time functions. Okay. Now we can argue that this objective function of the optimization formulation will have unique solution if the Jacobian is positive definite. That is, the Hessian matrix of this objective function, if that is positive definite, then there will be unique solution. So this we have been doing it several times. So we had done it for the case when there were two link interactions, and now we are saying it for the multi-link interactions here. So let us discuss the conditions on the travel time functions that actually ensure that the optimization formulation has unique minimum. Okay. So in order to ensure that this Jacobian matrix of the link travel time functions, which actually is the Hessian matrix of this objective function for this optimization problem. So in order to ensure that this matrix is positive definite, what are the assumptions that we need on the travel time functions? Okay. So similar conditions we had required for the two link interactions also. So now we are generalizing it to the multi-link interactions. So these conditions are as follows. First is that the travel time on each link is an increasing function of the flow on that link. Okay. So you take the derivative of the travel time on link A with respect to the flow on link A. So that should be positive. Okay. So this is the same condition that we had seen in the case of two link interactions as well. The other condition is that the main dependence of a link's travel time is on its own flow. That is, the derivative of the travel time on link A with respect to the flow on link A is much larger than the derivative of travel time on link A with respect to the flow on any other link. Okay. So this is this condition here. Informally stated, this condition is this, that is the derivative of travel time on link A with respect to flow on link A is much larger than the derivative of travel time on link A with respect to the flow on link B. Okay. Where B and A are not the same links. But actually more precisely this condition is this, that the derivative of the travel time on link A with respect to the flow on link A is greater than the sum of these terms here, where we have the partial derivative of the travel time on link A with respect to the flow on link B. Okay. Where we are summing over all the links B excluding link A here. That is what this means here. Okay. So note that these conditions here, that is the first one, that the travel time on link A is increasing function of the flow on link A, and this one, here ensure that the Jacobian of a link travel times is positively definite. Okay. So, notice here that when there are only two links that are present, then actually this condition boils down to this: dTA with respect to dxa is greater than dTA with respect to dxb. Okay. Because there is only one such link uh, B, which is actually A dash here. So, B is actually A dash here, okay, where the travel time on link A is actually a function of the flow. So, since TA is in the two link case, we had considered TA to be a function of xa and xa dash. So, we will just have one term here instead of this summation. Okay. Now, remember that when we were considering the two link interaction case, we had considered, instead of this condition, we had considered this, that dTA with respect to dx okay. So, we had considered this condition in the two link interaction case, but even if instead of this we consider this case, then also this will suffice. Okay. Okay, so let us now consider the shown 3-link network here. So, we have just made some modification in the travel time functions of these links here. These travel times of the first two links here have different expressions now. For the third one, it is the same here. Now, note that the partial derivative of the travel time on link 1 with respect to the flow on link 1 is equal to 2, and the partial derivative of travel time on link 1 with respect to the flow on link 2 is equal to 2 here. Okay. But since these two are equal, so this condition does not hold. Okay. But this condition is anyway holding, that the travel time on link A is an increasing function of the flow on link A. Okay. Now, since this condition is not holding, because this is equal to this, but we require that this should be greater than this here. So, it is possible that the Jacobian of the link performance functions may not be positively definite. Since the Jacobian of the link performance functions is the same as the Hessian matrix of this objective function, so we can alternatively also say that that may not be positively definite, and we can also check this. So, let us put together the Jacobian of the link performance functions here, which is actually the Hessian matrix of this objective function. So, this is what we get here. Okay. Now, this matrix is not positively definite, as the determinant of one of the left submatrix is negative here. Okay. Because the determinant of this will be 2 times 1 minus 2 times 2, which is equal to 2 minus 4 equal to minus 2. Okay. So, this matrix is not having positive definiteness. Okay. So, in this case, the equilibrium is not unique in terms of the link flows. Okay. And this can actually be shown by providing different solutions here. So, one such solution is that, suppose the flow on link 1 is equal to 0 and the flow on link 2 is equal to 5. Okay. Now, this is an equilibrium solution. Why? Because T1 star will be equal to 12 and T2 star will be equal to 9. So, let us quickly recall what are the travel time functions on these links here. And this is the travel time function on the second link here 4 plus 2x1 plus x2 here. So, if you fix x1 star to be equal to 0 and x2 star equal to 5, so the travel time on the first will be so the first link's travel time is equal to 12, whereas for the second link it is equal to 9. Okay. So, this is what we get. Now, this is an equilibrium solution. Why? Because the first link is not getting used at all, but its travel time is higher than the second link which is getting used here. So, because 12 is greater than 9 here. Okay. Another equilibrium solution here is that suppose all the flow takes place through first link and there is zero flow that takes place on the second link. Okay. And again that can be shown that this is an equilibrium solution, because when you do that, then here the travel time on the first link was what, 2 plus 2 times 5 plus 2 times 0, which comes out to be 12, and the travel time on the second link is 4 plus 2 times 5 plus 0, which is equal to 14. Now, here this second link is not getting used at all, but the travel time on this link is equal to 14. Okay, and this is greater than the travel time on the used link, which is 12 here on the first link. Okay. So, this is what it is saying, the travel time on the unused path is higher than the travel time on the used path. Okay. So, this last example shows the existence of multiple equilibria when the Jacobian is not positive definite. Okay. Even though the Jacobian matrix is symmetric. Okay. So, these two are different things here. So, just because the Jacobian matrix is symmetric, it need not be positively definite. Okay. So, there can be situations where equilibrium flow pattern is not unique. Okay. And also there can be situations where conditions such as symmetric interactions may not also hold. So, in all of this discussion that we were doing in the link interaction case, first we considered the two link interaction case and then we considered this multi-link interaction case. So, in both of these we had assumed that there are symmetric interactions. Okay. So, we had made, for example, in the two link interaction case, that the travel time on the first link, so if you take the derivative of that with respect to the flow on the second link is equal to the derivative of the travel time on the second link with respect to the flow on first link. Okay. And then we had extended that for the case when there are multi-link interactions. So, there the travel time on any link is not just dependent upon the flow on that link and another link, but also several other links. Okay. So, but there also we had assumed that the link interactions are symmetric, but there can be situations where these interactions are not symmetric. So, those cases are called asymmetric interactions. Those cases are much more complex to solve. Okay. So, for those cases it may not be possible to formulate an equivalent optimization program. Okay. So, we will not be discussing that, as that will be slightly out of the scope here, because those cases require much more complex algorithms. So, we will not be covering here. So, with this we will be ending the discussion on these equilibrium case with link interactions. Thank you.